afternoon and welcome to Mr. Michelbarra's Maths World. This is the way it is. Today we are talking about graphs of exponential equations and functions. And I think on one tape we'll fit dilation and shifts, and on another one we'll save that for reflections. Now, a dilation, we can talk about two sorts of dilations, parallel to the x-axis, and that's where we muck around. We put a scalar, if you like, a multiple in front of the exponential expression. I've got an example going there. And then parallel to the y-axis. We are going to dilate parallel to the y-axis by putting a coefficient in front of our x up there. And we'll see the kind of differences that those dilations have on a standard graph. Now, for the sake of this exercise, I've selected y equals 2 to the power of x. I could have selected y equals anything to the power of x. It would be an exponential function, including e to the power of x. Would have been a good one too. But anyway, let's see what happens when we start dilating by putting some numbers, some multiples in. So, looking at this one, well, our stock standard graph, y equals 2 to the power of x. When x is 0, y is obviously equal to 1, because anything to the power of 0 is 1. And when x is 1, just to take another convenient point, we would have, this is not to scale, it's not too bad, but it's not quite to scale. That does not matter for our purposes. So when x is 1, y is clearly 2. Now, let's have a look at the graph of that when we start multiplying it by numbers greater than 1. Numbers greater than positive 1, in fact. So, well, what happens is that you can see that, let's select another colour, that plotting this quickly, when x is 0, I've got 4 times 1 is 4, so up there. And when x is something else, maybe, well, 1 would be convenient, but it's going to be off my scale. 2 to the power of 1 is 2, 2 times 4 is 8. So I'd have to extend this up to my nice, that's supposed to be red. Let's put 8 up there. And extend it up from 1. So what's going to happen is that we're going to have a exponential graph like so. Not very well done, I apologise for that. 4 times 2 to the power of x. Now what it's supposed to illustrate is that your exponential function, by multiplying it by a number greater than 1, is going to be dragged, as it were, towards the x-axis. Okay? So, and of course, similar things but opposite things happen if the number is, if the multiple is less than 1. So let's say it was a half. Y equals 4 times, half times. This is being irritating today. A half times 2 to the power of x. I could have written that as 2 to the power of x on 2, of course, but a half is the key point there, times 2 to the power of x. Well, when x is 0, what have I got? Y equal to 1/2. So I can put that in like so. And also when, so that's one plot point. When x is 1, I've got 2 to the power of 1 is 2, a half of 2 is 1. So when I've got another plot point about there, isn't it? Okay? And so the thing is, excuse this whiteboard today, it's being a bit badly behaved. These aren't parallel. As the value of the multiple increases, it's getting the curve is getting dragged closer and closer to the x-axis. So that's a dilation parallel to the x-axis. Now we can also do dilations parallel to the y-axis, and how that's going to go is that, and note, by the way, it's important to realise that these lines will never ever cross or intersect or cross. Okay, they'll stay separate. So why I point that out is because when we are talking about dilations parallel to the y-axis, a different picture emerges parallel to the y-axis. Let's consider this. Firstly, we'll have our stock standard y equals 2 to the power of x. And now what we're going to do is put multiples in front of the x. So let's consider this one here, e.g. y equals 2 to the power of 2x, let's say. Alright, here's my rather crude number plane. Let's put some key features in. And my stock standard y equals 2 to the x might be represented by that curve there. Again, we know that that point would be, coordinate would be 0, 1, and if I had 1 here, it would be 2 there, wouldn't it? Because 2 to the power of 1 is 2. Alright, so now we're ready to consider our second curve, which I might do in purple, because it's written in purple. And let's have a look. When x is 0, notice what happens. 2 times 0 is still 0, so y will equal 2 to the power of 0, which is 1. What about when x is 1? Okay, so you've got 2 to the power of 2, which is equal to 4. So, again, I'm under allow. Let's put 4 there. And I've got 2 points. Now I want another point. Let's put in -1/2. Okay, let x equal -1/2, because this is important. When x is equal to -1/2, what I've got is 2 times -1/2, which is -1, isn't it? So, let's just write this down before we forget what we're doing. -1/2. When I'm substituting -1/2 in, I'm going to get 2 to the power of 2 times -1/2 is -1. Well, we know that that's equal to, therefore, y will equal 1/2, isn't it? Okay? So when x is -1/2, y is equal to 1/2. Now, this doesn't actually prove it, the point, but what is going to happen is that I'm going to get this purple line crossing, intersecting, in this case, at the y-axis. Okay? So that dilation is parallel to the y-axis. That's different. When I start messing around with my coefficients up here, you're going to get your curves crossing when compared with the basic standard exponential graph. I'm sorry that that's not particularly clear, but the important thing is our curves are crossing at the y-axis. Alright, so that's y equals 2 to the power of 2x. I could do a similar one to y, well, let's do it then. What's a good colour? Blue perhaps. Y equals 2 to the power of x on 2. So what happens there is that you can probably imagine the opposite of what we just did. So my curve is going to look like that. Okay? Let's just make sure that it does. So let's pick some convenient, well certainly it's convenient to let x equal 0. And the same thing happens. 2 to the power of 0 divided by 2 is still 2 to the power of 0, isn't it? So it's equal to 1. So again, we're going to cross at the y-intercept. What about when x is equal to 1? Okay, when x is equal to 1, we've got 2 to the power of 1/2, And 2 to the power of a half is the square root of 2, isn't it? Okay, so which is 1.414, roughly speaking. So it's going to be about, when x is 1, it'll be about there. And you can pick a negative value, a convenient negative value, maybe -1. And what you'll find is that your curve is looking like so. That one is y equals 2 to the power of x on 2. And the top one, that's a bit misleading there, so let's rewrite that. That was y equals 2 to the power of 2x. Okay? So notice that all our 3 curves are intersecting at 0, 1, and intersecting and in fact crossing. Okay? So that's what happens when we do a dilation parallel to the y-axis, as distinct from the x-axis, like here, where the curves don't cross at all. Okay, so that might be enough for that tape. Thank you.